Okay, it can be a little challenging to calculate the A0 or AN and BN coefficients, or the CN and theta N coefficients mathematically. Fortunately, we have a tool like Octave that allows us to check our work. In particular, there's a function in the UE signals toolkit called FS Trig2 that allows you to evaluate a function using a certain number of terms in its compact Fourier series representation. There is an FS Trig1 that allows you to evaluate the Fourier series summation from the AN and BN coefficients as well, but here we'll use the compact Fourier series form. Of course, we can't use an infinite number of terms in the series, so this is actually an approximation to the series. I'll provide this script on the lecture site so that you can download it. Here, initially, I'm going to use 40 terms in the Fourier series summation, and here's the mathematical expression for the C0. You'll see that it matches what we derived, and then here is the corresponding expression for the CN coefficients. So again, I've created a little n vector here that goes from 1 to 40 in this case, and so I'll get the first 40, the amplitudes of the first 40 harmonics here, and the corresponding phase angles of the first 40 harmonics, as well as the C0 coefficient. I pass those into this FS Trig2, the C0 term, which is a constant. Cn is a vector, a 40 element vector, as is the phase angle. Also, what gets passed in here is the period of the waveform. In this case, it's pi. And then T1 is a vector of time points at which I want to evaluate the Fourier series. So this will return our approximation to the original function based on our Fourier series coefficients. So the rest of this, the next section of code actually just plots that, and then we're going to compare that result to what we get to the original expression. So this is the mathematical representation of the original function, and I use the generate periodic or genper function to create a periodic extension of this base function with the T0 period here is pi, so the base function is defined from 0 to pi, and plot that actually just using circles on the same graph to overlap. And there are two other subplots where I plot just the C0 and Cn coefficients. This is going to be the amplitude spectra, and a third plot then showing the phase angles. The phase angles here computed using the inverse tangent function or arctangent function are in radians, so I use the radians to degrees function to convert those to degrees. Similarly, you could just multiply the entire vector by 180 divided by pi. So let's take a look at the plotted result. So I'll run the script, and it produces the following plot. So again, the blue line here is our approximation to the function based on the first 40 terms of the compact Fourier series. The circles here are I'm evaluating the original function at certain instances of time, and again, if we've got good agreement, I should expect the Fourier series approximation to line up, correspond to the samples of the original function as defined by the circles, and they do. So I can be fairly confident that I've calculated my Cn and theta N coefficients correctly, because they line up pretty nicely. This next plot shows the amplitude spectra here. Again, it's plotted as a function of omega. It had a fundamental frequency of 2 radians per second. plotting 40 terms. So the highest harmonic term here is 80 radians per second. If you recall, our C0 coefficient was just about 0.5, and the C1 coefficient here is about 0.24. You can see here how the amplitudes drop off as n increases. See that they get down pretty close to 0 here after about 40 terms, and theoretically never quite get 0, but do get smaller and smaller. And then this last plot is the phase angle. Again, 0 phase angle for the DC coefficient, but then I think the next one was like negative 70 something degrees, and then they approach negative 90 degrees for increasing n, and so we see that in the plot of the phase spectrum. It's a little interesting to actually see what the approximation looks like with a fewer number of terms included in the Fourier series. That's easy to do. Just at the top of the script, we define the number of terms used in the Fourier series as 40. So I'll just change that to 1. So and replot the results. And okay, so here's the approximation with just one term. Actually, we've got the C0 coefficient in here, the average value, which is a constant. And so just including one term, we're going to get the best approximation to the original function using just the fundamental component. You see, it's not great in this case. We need to include more terms here. Of course, the amplitude spectra just includes the DC component and then the fundamental component at 2 radians per second, and then the phase angle 0 at the DC component and minus 70 something degrees at the first harmonic. So let's take a look at what happens when we change that to 2 and rerun this. See if I can pull up the plot. So this is just with 2 sinusoidal terms in that summation. Again, it's a pretty rough approximation, but it's starting to take the basic shape of the original function. So I'll double that again. Let's take a look at what we get. Again, the approximation is getting better, certainly. You can see here as I'm adding in more harmonic terms. Now I'm up to the DC and the first 4 harmonic terms. I can still see the amplitude here is significant compared to the C1 amplitude. Let me double this again. 8. Rerun this. Now we're starting to get a pretty good approximation to the original function, but there are certainly some differences, and certainly you can see some squiggles here in our approximation to the original function. And the original function is defined by these circles. And here I'm looking down at the amplitude spectra with 8 coefficients. I'm going to go out to the 8th harmonic at a frequency of 16 radians per second. You still see the amplitudes here dropping off. Double this to 16. Redo the plot. And now I'm getting visually at least a pretty good approximation to the original function. My amplitude coefficients here at the 16th harmonic is pretty small in comparison to some of the lower harmonic amplitudes. Double this one more time. This is now getting close to the original case that we used where there were 40 terms used in the approximation. Again, here, pretty good results, at least visually. I don't see the squiggles, except at these discontinuity points. There's some overshoot and undershoot there. That's called Gibbs phenomenon. We'll talk about that a little later in the course, but anytime there's a discontinuity, you'll see an effect like this in the Fourier series approximation. But the main point main reason I wanted to show you this is that we do have some tools to easily verify that you've done your Fourier series coefficient calculations correct, and you'll actually explore using these functions in your next project.